Hello everyone, today I am going to discuss about dimensional analysis. There is a chapter 2 of module 4 that includes introduction, derived quantities, dimensions of physical quantities, dimensional homogeneity, Rayleigh's method, Buckingham phi theorem, dimensionless numbers, similitude and types of similitude. First let's go for introduction. Dimensional analysis is a method of dimensions. It is a mathematical technique used in research work for design and for conducting model tests. So this dimensional analysis is concerned with dimensions of various parameters, and it is a mathematical technique that is used for designing research field and as well as conducting model tests like testing of prototype. It deals with dimensions of physical quantities involved in the phenomenon. All physical quantities are measured by comparison, which is made with respect to an arbitrary fixed value. For comparison, there should be fixed value. So those fixed values are called as primary dimensions or fundamental dimensions. So length, that is represented by capital L, mass, that is represented by capital M, and time, that is represented by capital T, are three fixed dimensions or primary dimensions which are of importance in fluid mechanics. If in any problem of fluid mechanics heat is involved, then temperature is also taken as fixed dimension. In addition to mass, length and time, we have to take temperature if the problem involves some temperature parameter. These fixed dimensions are called fundamental dimensions or fundamental quantity. So mass, length and time are called as fixed dimension or fundamental quantity. So secondary or derived quantities as the name itself indicates, those are derived from primary dimensions or fundamental dimensions. Secondary or derived quantities are those quantities which possesses more than one fundamental dimensions. For example, you can take consideration of area that is given by length into breadth, or that is a dimension related to length. So length into length, that is length square. So it is a combination of fundamental dimension. So area is derived quantity. You can consider again one more example, velocity. Velocity is denoted by distance per unit time. So that is, velocity is given by mathematical formula. There is a ratio of distance to time. So unit of distance is meter, unit of time is that is second. So meter per second. So in terms of dimension, it is for meter it is length, that is L, and for time, that is for second it is timed T. So L T to the power minus 1 or L by T. So density, that is given by mathematical formula, mass by volume. So mass is M, volume is V. So mass unit is kg, unit of volume is meter cube. Overall unit for density, that is kg per meter cube. In terms of dimension, it becomes L to the power minus 3. Then acceleration, that is given by rate of change of velocity, or that is equal to distance per second square. Distance per second square, unit of distance is meter, unit of time is second, that is second square, meter per second square. So in terms of dimension, it is L T to the power minus 2. The expressions L by T, M by L cube and L by T square are called dimensions of velocity, density and acceleration respectively. So those are the derived quantities. There is an example for derived quantity or secondary quantity. For primary quantity, examples are mass, length, and you can consider temperature and time. Now let us go for some of physical quantities, dimensions of physical quantities. The dimensions of most commonly used physical quantities in fluid mechanics are as shown in table. So first fundamental quantity, that is length, that is represented by capital L, dimension is L. That second one, mass, that is represented by symbol M, dimension is capital M. Then time, that is represented by symbol T, dimension is capital T. These are fundamental quantities or primary quantities. Next, geometric quantities. There are two geometric quantities. As we all know, first one is area, second one is volume. So area is represented by capital letter A, unit is meter square. So dimension, meter is SI unit of length, so it becomes dimension. In terms of dimension, it is L square. And volume, that is represented by capital V, unit is meter cube, so dimension becomes L cube. Next, kinematic quantities. We have around 7 kinematic quantities listed here. So first one is velocity, symbol is V, unit is meter per second, dimension is L T to the power minus 1. Then angular velocity, that is represented by omega, unit is radian per second. So radian has no dimension or no unit, so dimension becomes t to the power minus 1. Acceleration, that is represented by small letter a, unit is meter per second square, so dimension is L t to the power minus 2. Angular acceleration, that is alpha, represented by symbol alpha, unit is radian per second square. Again, radian has no dimension or unit, so dimension becomes t to the power minus 2. Discharge, that is represented by q, unit is meter cube per second, so dimension becomes L cube t to the power minus 1. Acceleration due to gravity, it has same SI unit as that of acceleration, that is represented by symbol g, and unit is meter per second square, dimension is L t to the power minus 2. Then kinematic viscosity, that is represented by symbol nu, unit, it has unit meter square per second, there is a SI unit, dimension becomes L square t to the power minus 1. Next, dynamic quantities. First one is force. Force, as we all know, a force is given by second law, Newton's second law. So that is force equal to mass into acceleration. Unit of mass is represented by small letter m. Acceleration is represented by small letter a. So unit of mass is kg. Unit of acceleration is meter per second square. So overall unit becomes kg meter per second square. So dimension is ml t to the power minus 2. Then second one is weight, that is represented by capital letter W, that is given by mass into acceleration due to gravity. So small letter m into g, unit for weight is kg meter per second square. So dimension becomes ml t to the power minus 2. Third one is density, that is represented by symbol rho, that is given by mass by volume, so equal to m by v. So unit of mass is kg, unit of volume is meter cube, overall unit becomes kg per meter cube. So density has dimension ml to the power minus 3. Then specific weight, very important, or it is represented by small letter w or gamma, that is given by the product of density into acceleration due to gravity. Density has unit kg per meter cube, acceleration due to gravity has unit meter per second square. So overall unit becomes kg per meter square second square. So dimension is ml to L to the power minus 2 t to the power minus 2. Next, dynamic viscosity, that is represented by symbol mu, unit is Newton second per meter square. As we all know, Newton is a unit for SI unit for force, but n is that is n is alternate unit of force. Unit of force is given by from formula F equal to ma. Yeah, for m it is kg, a for acceleration it is meter per second square. So overall unit becomes kg meter per second square. That is the alternative unit for Newton. Therefore, unit of dynamic viscosity is kg meter per second square, that is for Newton, into second divided by meter square, by replacing n by kg meter per second square. Therefore, unit of dynamic viscosity is kg second meter per meter square or kg per meter second. So dimension is ml to the power minus 1 t to the power minus 1. Next, pressure intensity, that is represented by symbol P, small letter p, unit is Newton per meter square or Pascal. Dimension of force is, again here there is the pressure has unit Newton per meter square. So you have to write first dimension of force. Dimension of force is from F equal to ma, we already obtained as ml into t to the power minus 2, just write down. Then dimension of pressure intensity is ml t to the power minus 2 divided by L square, that is for meter square. So overall dimension becomes ml to the power minus 1 t to the power minus 2. Next, modulus of elasticity, or that is the Young's modulus, represented by capital letter E, or bulk modulus, or that is represented by capital letter K. Unit that is same as pressure intensity, Newton per meter square. So dimension of force is ml t to the power minus 2. Therefore, dimension of modulus of elasticity or Young's modulus or bulk modulus is ml t to the power minus 2 divided by L square. So overall dimension becomes ml to the power minus 1 t to the power minus 2. Next, surface tension, that is represented by symbol sigma. Unit is Newton per meter. There is a force acting per unit area, per unit length. So dimension of force is ml t to the power minus 2. So therefore, dimension of surface tension is ml t to the power minus 2 divided by L, that is equal to m t to the power minus 2. Next, shear stress, that is represented by tau. It has same unit as that of pressure intensity or modulus of elasticity. So unit is Newton per meter square. Dimension of force is ml t to the power minus 2. Therefore, dimension of shear stress is ml t to the power minus 2 divided by L square, that is equal to ml to the power minus 1 t to the power minus 2. Next, work or energy. Work is represented by capital letter W. Energy is represented by capital letter E. As we all know, work is given by force into displacement. Unit of force is Newton. Displacement has unit meter. So overall unit for work becomes Newton meter or joule. Joule is an alternative unit for Newton meter or work. So dimension of force is, I'll go with Newton meter. Dimension of force is ml t to the power minus 2. Therefore, dimension of work or energy is ml t to the power minus 2 into L. So overall dimension becomes ml square t to the power minus 2. Next, power. As we all know, power is rate of change of work. So, or it is given by work by time, represented by capital letter P. Unit of power is watt, or that is joule per second. Joule is a unit of work, second for time, so joule per second. Or alternative unit for work is Newton meter per second. I'll go with Newton meter per second. Dimension of force is ml t to the power minus 2. Therefore, dimension of power is ml t to the power minus 2 into L divided by T. So overall dimension becomes ml square t to the power minus 3. Next, torque, that is represented by capital T. It is given by force into distance or F into R. So unit is Newton meter, force as unit Newton, distance as unit meter. So overall unit is Newton meter. Dimension of force is ml t to the power minus 2. Therefore, dimension of torque is ml t to the power minus 2 into L, that is equal to ml square t to the power minus 2. Next, momentum, or that is called as impulse, that is represented by capital M and given by mass into velocity. Unit of velocity is meter per second and unit of mass is kg. So overall unit becomes kg meter per second. So dimension of momentum is ml t to the power minus 1. Next, dimensional homogeneity. So dimensional homogeneity means the dimensions of each term in an equation on both sides are equal. That is, LHS should be equal to RHS. Thus, if the dimensions of each term on both sides of an equation are same, then that equation is called as dimensionally homogeneous equation. So unit should be same on both sides of the equation, then it is called dimensional homogeneity. The powers of fundamental dimensions, there are three fundamental dimensions here, m, l and t. On both sides of the equation will be identical, or it should be same for dimensionally homogeneous equation. Such equations are independent of system of units. Next, let us consider one example. Velocity. Velocity is given by v equal to square root of 2gh. As we all know, unit of velocity is meter per second. So dimension of LHS left hand side, that is for velocity. We know for velocity formula, that's distance by time. Distance is represented in fundamental quantity L and time is represented in fundamental quantity T. So dimension of LHS, or that is for velocity, that becomes L by T, or that is L t to the power minus 1. Next, unit of, for right hand side equation, let's go with one by one. Unit of g, that is acceleration due to gravity, is meter per second square, and h is, that is a head, so that is in meter. So dimension of RHS, that is equal to square root of 2gh, that becomes square root of for g, that is meter per second square. 2 is constant, you can just neglect that term. So meter per second square, L by T square, into h is in meter, so it becomes L. So L by T square into L, so that is equal to square root of L square divided by T square, or that is equal to L by T, or that is equal to L t to the power minus 1. So dimension of LHS equal to dimensions of RHS, so that is equal to L t to the power minus 1. Therefore, equation V, that is equal to square root of 2gh, is dimensionally homogeneous because both the sides of the equation, that is LHS equal to RHS, has same unit meter per second or same dimension L t to the power minus 1. So it is dimensionally homogeneous equation. So next problem, check whether the following equation with their usual notations are dimensionally homogeneous or not. First one, HF equal to 4F LV square divided by 2GD, and second one, that is for equation for power equal to gamma into QH. That was a question asked in June, July 2019. So let's go with solution. So first write down the expression HF equal to 4F LV square divided by 2GD. Unit of LHS, that is head, friction head, HF equal to meter. So dimension of LHS, for meter it is L. So unit of RHS, that's how you just write down the equation 4F LV square divided by 2GD. So there F is a friction factor and 4 is a constant. You can directly neglect those terms, 4F. The remaining term is LV square divided by GD. Again you can neglect 2. So unit of L is, that's length is meter, and velocity square, that is for velocity meter per second. So velocity square means meter per second whole square divided by acceleration due to gravity has unit meter per second square. So meter per second square into diameter, that is d. So it is into meter. So meter per second square into meter. So it becomes, you can just multiply meter into meter per second whole square, that becomes meter square per second square. So meter cube per second square divided by meter square per second square. So remaining term is meter. So dimension of RHS is equal to L. So as dimensions of LHS and RHS are both equal, so this equation, that is HF equal to 4F LV square divided by 2GD, is dimensionally homogeneous. Next, second case, power equal to gamma QH, but gamma you can replace, that is a specific weight, or small letter W, as I already told in the table. So that is equal to, you can replace gamma by rho g, so power becomes rho g QH. So unit of LHS, that is power, that is equal to watt or joule per second. So joule for work, that is given by work is given by force into displacement, force as unit Newton meter. So you can replace joule by Newton meter per second. So force has dimension, force as unit, that is given by mass into acceleration, kg meter per second square into meter divided by second. So that becomes kg meter square per second cube. Therefore dimension of LHS equal to ml square t to the power minus 3. So that is for LHS. Now unit of RHS, that is gamma QH. Gamma can be replaced by rho g, there is a specific weight, rho g QH. So unit of rho is kg per meter cube. Unit of g is meter per second square. Unit of q, as I already told, there is a discharge, meter cube per second. Unit of h is meter. So overall unit becomes kg meter square per second cube. Therefore dimension of RHS ml square t to the power minus 3. As dimensions of LHS and RHS equal, the equation that is given by P equal to gamma QH is dimensionally homogeneous. Next, let us consider one more equation, that is for capillary rise. So that is given by H equal to 4 sigma cos theta divided by gamma d, or H equal to 4 sigma cos theta divided by rho g d. That is, you can replace gamma by rho g, that is a specific weight. So unit of H is meter, that is capillary rise, so that is in meter. So dimension of LHS equal to L. Then unit of sigma, that is surface tension, is Newton per meter. There is a force acting per unit length. So unit of rho is, that is density, is kg per meter cube. Unit of g, that is acceleration due to gravity, is meter per second square, and unit of diameter, that is in meter. So therefore unit of force is kg meter per second square. Therefore unit of RHS, force term you are going to get in surface tension, so I wrote unit of force there. Unit of RHS equal to, so there is 4 sigma, 4 you can directly neglect, and unit of sigma is Newton per meter. In place of Newton you can write kg meter per second square. So kg meter per second square into meter inverse, that is a meter to the power minus 1, because Newton per meter, cos theta, that has no unit, divided by, that is rho has unit kg per meter cube, and g has unit meter per second square, and d has unit meter. So kg per meter cube, meter per second square into meter, that gives dimension meter. Unit as meter. Therefore dimension of RHS equal to L. So equation H, that is equal to 4 sigma cos theta divided by gamma d, is dimensionally homogeneous as LHS equal to RHS dimension. Next, there's a very important concept. Once they asked this question last semester, advantages of dimensional analysis. So what are the advantages of dimensional analysis? What makes you to go for dimensional analysis here? So some complex problems, first point, some complex problems from fluid mechanics are simplified using dimensional analysis problem. So you can simplify the complex problem using dimensional analysis. It gives functional relationship between variables in dimensionless terms. And I'm going to discuss about this thing in Rayleigh method and Buckingham's pi theorem. So it gives a relationship between variables in terms of dimensionless terms like pi terms. Next, it reduces number of variables involved in physical phenomenon. It greatly reduces number of variables or parameters that is involved in physical phenomenon. Next, the dimensionless parameters are used to make certain logical deductions about the problem. Like you can derive some correlations. For example, Nusselt number is given by Reynolds number to the power some power and into Prandtl number to the powers like n. So you can deduce some logical equations from dimensional analysis. So those are the advantages of dimensional analysis. Very important thing. Just note down these 4 points. Next, applications of dimensional analysis. So as we all know, one thing, first application, it is used to check the dimensional homogeneity of the equation, whether left hand side equal to right hand side. So you can check that thing using dimensional analysis by using fundamental or secondary quantities. Next, it is used to derive equations for phenomenon in terms of non-dimensional parameters like Reynolds number, Mach number. So as we all know, the definition of Reynolds number and Mach number. So those are the dimensionless terms that finds application. Reynolds number in forced or natural convection and Mach number in supersonic, subsonic and sonic flow. So it reduces the number of variables in a problem by grouping them in less number of dimensionless groups, which reduces the number of tests in model analysis. So by using this dimensional analysis, you can group the variables into some dimensionless terms. So that reduces the number of tests in model analysis that may be related to prototype analysis. So it is used to arrange the test in a model analysis in a systematic manner. So it tells like which parameter should be considered first. So this makes the test more economical and less time consuming. So advantage of this model analysis, that is because of dimensional analysis, it results in less time. So these are the applications of dimensional analysis. So here dimensional homogeneity, that is very important. You can expect either theory or problem related to checking of dimensional analysis, dimensional homogeneity. Then other thing is applications of dimensional analysis and problems related to Rayleigh or Buckingham's pi theorem.